Welcome back to the lecture series on electric motor and generator design. This is lecture number 2, and the purpose of this lecture is to acquaint you with the overall operational theory in practical terms for the 3 kinds of motors that we're planning to study in this series. This is the motor genealogy chart that we listed before, and we're going to study this induction motor, which is electronically controlled, and we're going to study this reluctance machine, which are electronically controlled, and then we're going to study both hybrid and permanent magnet, no, wait a minute, they're over here. Brushless DC motors over here we're going to study. Both sine drive and square drive, electronically commutated, okay? Then induction, we're going to show you how to design rotors for those to get good performance with a stator. This is a very interesting slide that compares machine cross sections to give you an idea what these three machines look like in concept anyway. This was developed a number of years ago by Professor Tim Miller from the University of Glasgow, my co-author for a couple of books that we've written on brushless machines. But you'll notice that this little chronology starts with the commutated DC motor. Here's your field windings in the stator, and then your armature windings on the rotor. And those are the commutator bars there, and these represent the brushes. So each one of these coils is here's one pole, there's the second pole. So that means that the coils are going to be wound across 180 degrees apart. There'll be a coil there and a coil there, and then pairs of those coils wrapped, stepped all the way around in a lapped fashion. So as this rotor rotates, see, when the current is applied into those coils, it causes the polarity of those coils to be such that they move. That will put that torque component on the conductor, which pushes against the steel teeth of the rotor and causes it to rotate. So it commutates itself, it rotates, but then as soon as it rotates, why, it shorts out the next bar and energizes the next coil and shorts out the one before it. So rotation is continued. If you reverse the polarity of the voltage across these two terminals or across these two terminals, you change the polarity of the flux generated by either the stator or the rotor. If you have permanent magnets here, then you just change the polarity of the armature. Now, what's interesting to note, even by looking at this picture, is down here we have a permanent magnet version of this. Here's a permanent magnet version of that. Instead of this wound electromagnet, North Pole and South Pole here, we have a permanent magnet. Now, there's no wires connected to that, so the flux from this permanent magnet is fixed. The field, or the flux that comes from this electromagnet, can be adjusted. So if you connect a DC power supply across here, you can vary the strength of this field and vary the whole torque speed curve and characteristics of the machine. But on the permanent magnet machine, you don't have near that flexibility because your magnetic field is fixed. It's not adjustable. You can't make it stronger or weaker. But these DC motors evolved into synchronous motors. Remember, that was our second motor. It was an AC synchronous motor. It has a wound field on the rotor, much like the wound field on the stator of a DC machine. So this rotor produces DC current flows in these coils, producing north-south poles, and then the flux from those electromagnet poles in the rotor link with the conductors in the stator, so you have a synchronous motor. The brushless version of that's this one, replaces these wound field coils with permanent magnets, the same way that DC motor, the permanent magnets in the stator replace the wound electromagnets in the stator. In the case of the synchronous machine, the wound poles in the rotor are replaced by permanent magnets on the rotor. So that's why it's called a synchronous machine, even though originally it was called a brushless machine, because it originally was an inside-out version of this machine, which we'll see in an upcoming slide. Now, take this same motor here with the magnets on the surface. This is an SPM, surface-mounted magnets, we call those. If you take the rotor core and put slots inside of it, instead of having the magnets on the surface, you stick them on the inside. You have, that's now known as a brushless permanent magnet AC machine, or permanent magnet synchronous machine. And so you get torque from the magnets, but you have some little steel poles in between the magnet poles here, and you can vary how big those are. You can adjust the reluctance torque component you get from those poles that are those soft iron poles that are between the magnets. Didn't mean to flip that slide so quick, but since we did, we've got to start talking about this. These motors are, well, maybe I could go back. Yeah, let's go back and finish this. Let's do it that way. That's better. In this case, the last thing I wanted to show you about this was of course the induction machine, which has the same stator as this guy, but it has a different kind of a rotor in it. And we're going to talk about what that rotor consists of. That's a punch lamination with slots in it, and those slots are filled with current carrying conductors. There's a couple ways you could fill it. You can wind them, or you can cast them in there. Now, this machine here has the same kind of a stator as these other machines we talked about. See, they all have the same stator, but the rotor is different. It's made up of pieces of steel and air, or steel and plastic, or steel and magnets even. But so the steel part are called magnetic flux carriers, and the air sections, or plastic sections, or fiberglass sections, or whatever you want to make them out of that's non-magnetic, those are called flux barriers. So if this is a direct axis, the inductance of the phase windings in this axis are high because there's lots of iron in the circuit, but in quadrature, or 90 electrical degrees, this is a 4-pole machine, so it's 45 degrees mechanical. This is a quadrature axis, so the inductance of the phase is low in that axis because there's a lot of flux barriers radially from the shaft out in that quadrature direction, you see. And now here's an extreme example of a reluctance machine that has poles that look like a gear on the rotor and poles that look like gear on the stator. So if you look at this winding here, the flux is going to go through there like that. There's very little air gap in the circuit. It's all iron, very tiny clearance gap there. But in this set of poles, there's lots of air gap in the circuit. You got this great big air gap in there. So the inductance here is very low, and the inductance there is very high. There again, we're in quadrature here. So in reluctance machines, the torque and performance you get is based upon how well you can create this saliency, or how well, or how big of a difference you can design into the geometry such that the one inductance is a lot higher than the other one. So the inductance ratio is equivalent to the saliency ratio in these kind of machines. So that's what I wanted to point out. But we're not studying the switch reluctance machine in this series because it uses a different stator, different winding. It's a whole different design topology. So it's not easy to compare it with these other machines. We'll have to treat that as a separate topic all by itself. Okay, now the purpose of using these old motors in new ways using power electronics is to vary the speed and determine whether the torque or speed is positive or negative. So if we plot torque on the horizontal axis, and here's zero torque, so we could produce clockwise torque or counterclockwise torque. That's like pedaling your bicycle frontwards or backwards.